So working with relative error helps us get an idea of how the error relates to the size of the object that we're working with. Because we're always going to have some error in there. We just need kind of a scale for how significant that error is. So let's say I said I was measuring something and there was an error of 5 grams from the measurement and what I expected. Your next question might be, well, what were you weighing? What had this 5 grams of error? If I said it was like a pill for medication, that might be kind of alarming because 5 grams of a drug can make a very big difference. Whereas if I said I was weighing a car and there was a 5-gram difference, you'd be like, oh, that's nothing. So there's this idea of how does the error compare in scale to the thing that you're measuring? And that's where percentages are going to come in. We're going to relate this amount of error we're seeing as a percentage of kind of what we expected to get out. So we're going to have these pieces. One piece is going to be this idea of an expected outcome. What did we expect from our measurement when doing it? Another piece is going to be our actual measurement that we take. And that measurement is where we're going to be seeing some error come through. Because what we want to do is compare those two things. So that's where absolute error comes in. It's going to be this difference between the measurement that we take and the expected outcome. So what the difference between those two values are, that's our absolute error. So instead of looking at the absolute error, like my example up above there that I was describing, if I said there were 5 grams error, that would have been describing an absolute error. And that's where we don't really get a sense of the scale of the thing that we are measuring, like how bad is that 5 grams error? And that's where relative error comes in. What we do is we take that absolute error and divide by the expected outcome, and what we get is a percentage of error. Then we can see, like, if that 5 grams was with the weight of a pill, maybe that would be like 80% error or something extreme like that. It would be a lot of error. Whereas with a car, maybe that would be like 0.01% error. It would be nothing because a few grams difference of a car doesn't change all that much. So we want to get to this calculation of relative error to give us a better idea of how far off are we in terms of the scale of the thing that we're measuring. So for example, we're going to look at an 8.5 by 11 inch piece of paper. So those are our expected values there. So we have our width and length, and that's what we expect to come out when we measure it. What happened is we measured it, and the length, instead of being 11 inches, we saw that it was 11 1/8 of an inch. So this right here is our measurement, which has a little bit of error to it. But what we want to know is this little bit of error that we're getting, how big of a scale is that compared to expecting an 11-inch measurement? So determining the relative error. If it helps, you can start with the absolute error, or you can do this all in one big calculation too, kind of like our percent change that we did in the previous videos. If you want to, you can just plug in measurement minus the expected outcome divided by expected outcome. And that's what we're doing here. So, relative error. We're going to take our measurement, which is 11 1/8 inches. Now what I'm going to do is, because we're trying to get a percentage out here, what we're going to do is we're going to be working with decimals. So worrying about fractions here isn't worth it. So if it helps, what you can do is change this to a decimal if you want to work it within that way, or just completely rely on the calculator. But what I want to do is show you that if you want the decimal form of this, so 11 1/8 inch, so you could do is just get the decimal for 1/8. So if it's 11 1/8 of an inch, then you're just adding that 0.125 onto 11. You could even do the whole math in here of that is the equivalent of 11 and 1/8 inch. So this is really in 11.125. So I'll just make the math a little simpler. So we take our measurement, which is 11.125, minus the expected, which is 11, all divided by 11. And we just plug that into a calculator. So the calculator is going to give us a decimal, so 0.0113636. And that's our decimal form. So to change it to a percentage, so that we get this idea of percentage of error, I'm going to move my decimal to the right 2 spots. So I'm going to go to, let's say, 2 decimal places. So I'm going to do 1.14%. Ooh, nearest tenth of a percent. So actually that's just going to be a 1.1%. And that would be our relative error. So that doesn't seem too bad. It's just like about 1% error, not too extreme coming through there. All right, we're going to look at that same piece of paper. When we look at the width, we got 8 5/16 of an inch. So this right here is our measurement where we expected 8. So I'm going to get the decimal there, which if you put 5/16 into a calculator, it should be a 0.3125. So getting out relative error, we're going to take the measurement minus the expected divided by expected. And in terms of a decimal, that will be a 0.0. I'm just going to write some numbers down from the calculator. And we're going to move our decimal over. So we're going to go 1, 2. And then we're rounding to the nearest tenth of a percent. So this will be a 2.2%. So in terms of scale of things, we're seeing a little bit more error with the measurement of the width compared to the length that we did up above there. But in terms of amount of error, 1 or 2% isn't too bad.